In this video, we're going to be talking about something called parametric equations. By way of explaining what that means, I'd like to invite you to come along with me on something of a thought experiment. Let's say we have the equation of a line y equals negative x plus 1. Now, I hope by now you all know how to graph that. It has a y-intercept of 1 and a slope of negative 1. So let's make this our scale of 1. I'll put my y-intercept there, and then my slope of negative 1 means I need to come down 1 and over 1 to find another point. Once I have 2 points, I can connect them, and I have a line. Now I know quite a few things about this line. I know about the y-intercept, which is the value of y when x equals 0. I suppose I should label my axes here. This is my x-axis, this is my y-axis. The value of y when x is 0 has some important implications in commerce, for example. There's always the point 0, comma b for some value, some value of b, some y value. The x-intercept right here is important in telling us something about where the graph changes from positive to negative, where the y values change from positive to negative. I can tell you about its slope, which is a rate of change. That's something you'll meet more in calculus. But for now, suffice it to mean that there are a lot of important things that we can do if we know the slope of a line, especially in applications. One thing I don't know about this line is where it started and which direction it's going in. All I know is that there's a record of the final product here on the screen. This is the thought experiment part. I'm going to change the way this equation looks by doing some algebra on it. And it's basically backwards from what we're going to be doing in this topic. I want to show you where this idea of something called parametric equations is coming from. So I'm going to start by multiplying both sides of this equation by 2 and then distributing. That should actually be a plus. Now I'm going to subtract 4 from both sides. Bear with me. That's an equals. Plus 2 minus 4 is minus 2. Now I'm going to refactor. Take the 2 out of both sides. Oh, I left my negative off on this side here. Factor a 2 out of the left-hand side and I get y minus 2. Factor a negative 2 out of this side and I get an x plus 1. And then I'm going to divide the right-hand side by positive 2 and the left-hand side by negative 2. I'm effectively uncross multiplying for those of you who are comfortable with that terminology. And let's see, I get x plus 1 over 2. Now, I've got two expressions here that are equal to each other. I could have done this at any point along the way, but I'm choosing to do it here for a reason, so just bear with me. At this point, I have two expressions rather, that are equal to each other, and so I'm going to say that both of them are t. They're both equal to t. So I have t is equal to y minus 2 over negative 2, and t is equal to x plus 1 over positive 2. Now I'm going to continue with my algebra. I'm going to multiply both sides by negative 2. Here I'm going to multiply both sides by 2, and so on. So let's start with the first one. Negative 2t equals negative 2 divided by negative 2 times y minus 2. Now I'm going to add 2 to both sides. So I get negative 2t plus 2 equals y. And on this side, for this other equation, I get 2 times t equals x plus 1. Subtracting 1 from both sides, I get 2t equals 2t minus 1, 2t minus 1 equals x. So I have x is equal to 2t minus 1, and y is equal to negative 2t plus 2. And I got these two equations from a single equation that had both x and y in it. I played around with it until I got two expressions, one on each side, one that had just a y in it and no x, and one that had an x in it and no y. And then I set each of those equal to some third variable t. Now, when I look at this pair of equations let's make a table. That's how we first learned how to graph lines, right? I'm going to have a table with an x and a y in it. But instead of picking an x and letting x define what y is, I'm going to pick values of t. Let's go 0, 1, 2, 3. Not sure where I'll need to go after that, so I'll leave that for now. If t is 0, I can plug t in both of these equations, and it'll spit out an x for this one and a y for this one. So let's try that. If t is 0, I get 0 minus 1. So x is negative 1 when t is 0, and I get a 0 here as well. Y is 2 when t is 0. This is the point negative 1, 2. On my graph up here, if I go to x equals negative 1, and I go up 2, lo and behold, there's a point on my graph that is negative 1, 2. Let's do this for a different t value, see what happens. If t is 1, then here I get 2 times 1, which is 2, and 2 minus 1 is 1. So when t is 1, x is 1, but what is y? When t is 1, I get negative 2 plus 2, that's 0. So now I have the point 1, 0. Let's check that on our line. 1, 0. Now, not only am I getting the same line by doing this, I can see exactly where that line starts. In fact, at this point, I would argue that this arrow is now redundant. It's worse than redundant, it's wrong. Let's actually do one more of these. Let's let t be 2. If t is 2, here I get 4 minus 1, which is 3. That's my x value when t is 2. And I get negative 4 plus 2, which is negative 2. That's my y value when t is 2. The point 3, negative 2 is about there. And my graph isn't quite long enough. Let me just erase the arrow and extend it a little bit. And then I have the point 3, negative 2 also on this line. So as you can see, when t equals 0, my first point, the first point I plotted was right here at negative 1, 2. That was the first point I plotted because t was equal to 0. That was my starting place. After that, I plotted 1, 0, and then 3, negative 2. So I plotted this point, and then this point, and then this point. So not only do I know where my graph starts, but which direction it goes in. For much of what we do in algebra, this is overkill. We don't necessarily need to know where the graph starts or which direction it goes in. In fact, the other thing I can tell from this is how fast it's moving, but we'll talk about that a little bit later. Most of the time, we don't need that. Just having a record of where the line is on the page is enough, but sometimes we need more information. We need this extra layer. And so what we call this pair of equations here is, we call them parametric equations, because in order to graph the same, basically the same information that we had with just this version, we had to introduce this third variable. We call that third variable a parameter. T, wrong color pen, hang on. T is what we call a parameter. And so this pair of equations is a pair of parametric equations. It's important to note that the t in both of these equations is the same thing. Notice that when I plugged in 0, I plugged 0 in for both of these, and that's how I got my x and y values for the point at which t was 0. T is often, and the reason we use t as our parametric variable, t is often time. So if I say I'm going to start at t equals 0, that means I'm starting at the point in time when time is 0, if that makes sense. It's a bit redundant. Imagine that you're clocking an experiment or something, and you start a stopwatch. The instant you start that stopwatch, that's t equals 0. And as the clock runs, t moves on, and as t goes on in time, as the parameter moves up in time, x and y change accordingly. So t is the parameter. This is a pair of parametric equations, and the rest of this video is pretty much about that. So before we move on to other things, let's do another example of graphing with the parametric equations. In this example here, I took a regular graph of a line and I broke it up into two equations first. I introduced a new parameter. I introduced a new variable here. And then we graphed the parametric equations. But in the next video, or in the next slide rather, I'm just going to give you the parametric equations, and we're going to work together to see what the graph of that pair of parametric equations looks like. Sometimes when you see a pair of parametric equations, you'll also see a curly brace like that. That sort of helps identify them as a pair, a matched pair. All right, I'm going to do the same thing here. Whenever we learn a new graphing skill, it's often the case that we make a table of values. I don't know how many values I'm going to need here. I suspect I will need maybe 4 or 5. I don't think I'll need too many more than that. So let's go t, because that's the parameter. That's the thing I'm going to plug into the various different, to the two different equations. That's probably enough. When I plug t into this equation, it will produce an x value. When I plug t into the same t into this equation, it will produce a y value. And it's that pair of values, x comma y, that I'm going to plot, that I'm going to graph on the grid I have over here. I happen to know this one's going to be in quadrant 1. They won't always be. So let's start with our 0. If I plug 0 in here and 0 in here, I get 0 plus 4, which is 4, and 0 squared plus 1, which is 1. So x is 4 and y is 1. When I plug 1 into my x equation, I get 1 plus 4, which is 5. When I plug 1 into my y equation, I get 1 squared plus 1, which is 2. Plugging 2 in gives me 2 plus 4 for x, and 2 squared plus 1, 4 plus 1 is 5 for y. Let's do at least one more. 3 plus 4 is 7. 3 squared plus 1 is 10. That may be enough, so let's just stop there for now. If we need another point or two, we can come back and get them. All right, now I'm going to plot these points, but the points that I'm going to plot are these ones. The t value is how I got those points, and the t value is going to inform my final graph in that I'll have to refer back to it to figure out where I started, which direction I'm going, and so on. But once I have my points, the actual job of plotting them is just like plotting points on a regular old-fashioned graph of x and y. The points I have are 4, 1, which is about there, 5, 2, which is about there. So far, it looks like it might be a line. 6, 5, oh, it's not a line. And 7, 10. I think that's perfect scale-wise. Now, it's tempting to draw a line that sort of goes in that direction and then goes on and on until forever, right? And I don't know what's going on down here. I actually do, but I'm gonna withhold that information for the moment. I don't know what's going on down here, so I kind of just have to put an arrow and say, well, maybe it just goes in that direction forever. But here's where one of the big differences is between parametric equations and regular old-fashioned linear equations. And that is that the parameter tells us that we should start at 0 with this point right here. There's nothing above this, which means there's nothing before this point. So I'm actually going to erase, oops, my eraser's too big. I'm going to erase this part of the graph because the parameter tells me that the first point on the graph is 4, 1. That's the first point. There's nothing before it. I don't know what the last point is. There are times when it might be told, for example, that t goes from 0 to 3. In that case, this is the last point, and I should not try to plot anything else. And that means erasing this part of my graph as well. Now there's one more thing that I can do here, and that is indicate in the graph where I start and what direction I went in. The direction's easy. I'm just going to add a little arrow. And in fact, that implies the start and the end as well. If I'm going in this direction, it must be the case that I started here. And if I'm going in this direction, it must be the case that I'm ending here. Now, sometimes you'll have an end limit to your parameters, and sometimes you won't. But in this case, I've introduced that to let you know that there are sometimes limits. So that's it. This whole thing right here is my graph. Now what I'm going to do is undo the process that I did a few minutes ago on the previous slide. I'm going to take these two parametric equations and I'm going to create a single equation out of them. And the way that I'm going to do that is I'm going to solve this equation for t. I'm going to do that down here. I get x minus 4 equals t. And I'm going to plug that in to this t. Y equals t squared plus 1, but t, I now know, is x minus 4. And when I simplify that, I get x squared minus 8x plus 16 plus 1 is plus 17. And lo and behold, I have a quadratic. And that's exactly what this is. It's a piece of a quadratic equation, a piece of a parabola. In fact, if I hadn't expanded it, I'd be able to tell you exactly what this parabola looked like just by looking at its equation. This is algebra I'm doing now. It's got a vertex at 4, 1, which is right here. That's actually, I need a different color. How about green? That shows up a little bit better. That's where the vertex of this parabola is. It doesn't have a coefficient, so it's kind of a normal parabola. It's not stretched or shifted or any, it's shifted, but it's not stretched or compressed. And a parabola would go up in both directions. It would go up on the other side as well. It would go up forever. That's what the parabola would look like. But because it's a pair of parametric equations, I only want this part of it. And that's defined by the parametric equations. There are times when this is important. So knowing that your parametric equations will give you just the part of the graph that you need and nothing else, knowing how to graph that, knowing how to interpret this is a really important skill. This is pretty much all we need to do for this topic. This topic is just about what parametric equations are and how to sketch them if you have the equations. In this case, we have the parametric equations and we've drawn a graph. I do want to make one point before we move on, and that is that you can have a parameter of t equals -1 or -2 or -7.5. You can have negative t values. That does happen. It's possible. In this case, and in many cases, we started at t equals 0. And it's sort of implied here that we don't have anything less than that. But it does happen. It does come up. So be prepared for that possibility. One of the things you might be looking at there is the path of a particle or something. And you might want to know what happened 3 seconds before you started your stopwatch. That's what we would mean by t equals -3 in a case like that. So that's pretty much it for this video. The next one, we're going to be talking more about this process here, which is called eliminating the parameter.